Okay, I think that's 2 o'clock. Welcome back. So we're going to continue talking about what we were talking about yesterday. So you remember essentially the last thing that we came up with, I guess, is, well, sort of two things. The first is a relationship between the null space and the row space, right? So this theorem 4710 tells us that the orthogonal complement of the row space is the null space, and therefore the orthogonal complement of the null space is the row space. They're orthogonal complements of each other. And what that means is if you take anything from the row space and dot it with anything from the null space, you get 0. Right? So everything in the row space is orthogonal to everything in the null space. And because of this general decomposition theorem we're going to prove later, that allows us to decompose, in this case, Euclidean n space into the direct sum of any subspace and its orthogonal complement, that immediately tells us that Rn, you've got some n by n matrix, Rn is the direct sum of the row space and the null space, and Rm is the direct sum of the column space and the co-kernel, null space of A transpose. Okay, so what we want to do today is use these facts to understand what the set of all solutions to some linear system looks like. Right? So we're going to consider an arbitrary linear system and understand, characterize the solution sets in terms of these subspaces. So the first thing that I want to show, using an argument that's kind of similar to something we did yesterday, is that you take any matrix you like, any n by n matrix. If you take any element of the column space, right, and we know that if you want a consistent linear system, if you want AX equals B to be consistent, you've got to pick B to be in the column space. So you pick any B in the column space, and the claim is that there's a unique thing in the row space, right? Not just there is something in the row space, there's a unique thing in the row space such that the set of all solutions to AX equals B, right? So you specify B, some sensible B where AX equals B is going to be consistent. The set of all solutions to this equation is precisely this, right? It's this unique P that lives in the row space plus any element of the null space, okay? So you can consider this to be some kind of shift of the null space. You take the null space and you add this unique thing from the row space to it. You get something that's not actually a vector space, unless P happens to be 0, but it's a well-defined set living in Rn. And the point here is that this P is unique. So for every B, there's a corresponding P. We've already proved something sort of like this. We proved that if you had any solution to a linear system and you added something that was a solution to the homogeneous equation to it, you got another solution. Right? We've already proved that, but this is more precise than that. This is saying there's only one thing outside of the null space that is sort of really your solution, and then every other solution is just that unique thing with something from the null space added to it. Right? So you might have seen this in some first-year calculus course to do with differential equations or some engineering course or something. This P here is what would be called the particular solution in that context, right?
So it's just a generalization of the solution being a particular solution and a homogeneous solution, right? This is like a generalization of it. Would that be?
So say that again, a generalization of what?
Would this be a generalization of like the x is equal to the particular solution plus a homogeneous solution?
Yeah.
And x plus b.
It's not really a generalization of it, it's a more precise version of it. What we said previously was that if you had a solution, you could add a homogeneous solution to it and you still got a solution. But now we're saying there's only there's like one unique solution that's outside the null space. That's your particular solution. Every other solution is that thing, which lives in the row space, plus something from the null space. So it's sort of a more precise version of what we had previously. Okay, so what we really need to do is show that this P is unique. Okay, that's going to be the important thing to do. All right, now, we know Ax equals B is consistent if and only if B lives in the column space, and we're assuming B lives in the column space, so this equation is going to have solutions. All right, so we already showed this, that X equals B is consistent if and only if B is in the column space. So we know by this assumption here that our equation is consistent. Right? And it's consistent now for everything in every choice of B in here. All right, so now what's the key observation? Let's forget about whether or not X and Y are solutions for the moment. Let's just pick two things in Rn. Now, we know for any matrix A, we can decompose Rn like that. Right? So if I take any X or Y in Rn, I know I can write them as something from the row space plus something from the null space. That's what we showed yesterday. And I know I can do that in a unique way, right? So each X in Rn, forget whether it's a solution to our equation or not, can be written as a unique thing from the row space plus a unique thing from the null space. So our corollary from yesterday, 4, 7, 11, tells us that we can write X as P plus Z and we can write Y as Q plus W. Where P and Q live in the row space and Z and W live in the null space. Okay? So now, I haven't assumed anything about X and Y yet, except they live in Rn. But now let's assume that they're both solutions to our equation Ax equals B. And we know that thing has solutions because B is chosen to be in the column space. So now let's say X and Y are solutions. So that means B equals Ax and B equals AY. Okay, but what's X? X is P plus Z. And what's AZ? 0. AZ is 0 because Z lives in the null space. So this is AP plus 0, which is AP. And likewise, AY is Y is Q plus W. This is AQ plus AW. And what's AW? AW is 0 because W also lives in the null space. So this is AQ plus 0, which is AQ. So now, what do we know about AP and AQ? They're equal, right? Because they're both equal to B. So what we've learned is that if X and Y are solutions to Ax equals B, then AP and AQ have to be equal. So AP equals AQ. Now, what does that tell me about where P and Q live? So by assumption, P and Q live in the row space, but this equation tells me something else about where they live too. The null space? Why do they live in the null space? And I guess my question wasn't really well posed. So it's not so much about where P and Q live, but where does P minus Q live? I guess that's what I should have asked. Where does P minus Q live? In the null space, right? So I can simplify this equation right, by taking AQ over the left-hand side. And so this tells me that P minus Q is in the null space. Okay? So arguing as we did yesterday, right, I know P minus Q is in the null space, but I also know something else about where P minus Q lives. Where else does P minus Q have to live? The row space, right? Because P lives in the row space and Q lives in the row space, and the row space is a vector space. So if I take any linear combination of P and Q, it also lives in the row space. P minus Q is just some linear combination of P and Q. So P minus Q also lives in the row space. So we've just seen that it lives in the null space by direct calculation, but it also has to live in the row space because the row space is a vector space. All right, so this is basically the same argument as yesterday. The row space is a subspace. So because it's closed, P minus Q also lives in the row space. So it lives here and it lives here. So P minus Q lives in the intersection of the null space and the row space, because it lives in both of those spaces. But the row space is the perp of the null space. And what does the intersection of W and W perp contain? 0, right? That's all it contains. So we showed that yesterday. So that means P minus Q is in fact 0, which means P equals Q. So what we've shown is that if you take two solutions to AX equals B, you decompose them into something from the row space plus something from the null space, which we can do for any vector in Rn, then you find, after a little bit of doodling, that the thing in the row space had to be the same in both cases. So every solution to AX equals B is the sum of the same thing from the row space plus something else from the null space. Okay? So you can generate every solution to AX equals B by taking the unique thing in the row space that satisfies AX equals B and then adding absolutely anything from the null space to it. Okay? So it's a way of generating all of the solutions to your equation. So we've got this kind of, I think, nice, somewhat sort of abstract characterization of a very elementary question, right? It's a very elementary question people have been thinking about for hundreds or probably thousands of years. I'm not an historian. What's the set of solutions to some linear system? Here's how to characterize it using this abstract vector space stuff. All right, so every solution to AX equals B looks like X equals P plus Z with Z, any old thing from the null space you like, but you have to have the same P in the row space. Okay? So the point here is that we've got this one-to-one correspondence between the P's and the B's. Right? For every B in the column space, you get a unique P in the row space. So the row space and the column space are really talking to each other. All right, so I want to make one statement about, or one more statement about the co-kernel now, right? So we've sort of understood basically what the domain's doing, if you like, right? The domain of our transformation with standard matrix A, you can decompose its domain into the row space and the null space, and we sort of understand what the null space and the row space are doing. The row space is where the particular solutions live, and the null space is where the homogeneous solutions live, and everybody in the domain can be written uniquely as something from that particular solution space and something from the null space. But what's the point of the co-kernel? The point of the co-kernel is that your equation, Ax equals b, is consistent for all right-hand sides if and only if the co-kernel is just a single point 0. Right? So what this is trying to get at is that the size of the co-kernel is telling you how non-surjective your transformation is. It's sort of telling you how many things in the codomain aren't images. It's like the size of the co-kernel determines how many things you can generate that live in the codomain that aren't images. So it's not just the set of things that aren't images, right? The set of things that aren't images are going to be everything from the column space plus something non-zero from the co-kernel. But it's sort of the size of the co-kernel tells you how non-surjective your matrix transformation is. Okay, so the proof of this is quite straightforward. It's basically just a restatement of the fact that Ax equals b is consistent for all b if and only if the column space is Rm, right? And because we know we can write Rm as the direct sum of the column space and the co-kernel, if the column space is all of Rm, the co-kernel, which means the column space is as big as it can be, means the co-kernel's got to be just the point 0, i.e. as small as it can be, right? Because Rm is always sort of the direct sum of these two spaces. If you want column space to be as big as it can be, co-kernel's got to be as small as it can be. Okay, so Ax equals b is consistent if and only if b is in the column space. So we're considering the case where the system is consistent for all b. So Ax equals b is consistent for all b in Rm if and only if the column space is Rm. Now, from what we saw yesterday, we know that the co-kernel, which is the null space of A transpose, is the perp of the row space of A transpose. And be careful here with these T symbols because they're doing completely different things, right? This one, which acts directly on the A, is just transpose. This upside down T acts on a vector space because it's the perp. So they're completely different symbols, completely different meanings. But the null space of A transpose, or the co-kernel of A, is the perp of the row space of A transpose. Just because A transpose is just some other matrix. This is just using theorem 4.7.10. But the row space of A transpose is the column space of A. So the co-kernel of A is the perp of the column space of A. So Ax equals b is consistent for all b in Rm if and only if the null space of A transpose is not Rm, but the orthogonal complement of Rm, right? So if you want the column space to be all of Rm, the co-kernel has to be the orthogonal complement of Rm. The orthogonal complement of Rm is the set of all vectors that are orthogonal to absolutely every vector in Rm. Now, how many vectors are orthogonal to every single vector in Rm? Somebody yell out at me. Who wants to put their hand up? One. Which one? Zero, right? The only thing that's orthogonal to absolutely everybody in Rm is the zero vector. So this is just the zero vector space. So that's actually on the problem set. Right, the perp of Rm is just the trivial vector space. Okay, does that make sense? So the size of the co-kernel is telling you how far away your transformation is from being surjective. Of characterizing how big the set of non-images is. Okay. Here's a picture that is supposed to try and start summarizing this stuff. Okay, now let's try and interpret what the hell this thing means. All right, so on the left, what have we done? We sort of forget about the arrows for a second. On the left, we've just decomposed Rn into the row space and the null space, right? So what we're saying is that everything in Rn is can be written uniquely as something from the null space plus something from the row space, okay? Now the reason I've drawn these squares or rectangles or whatever they are at right angles is to emphasize the fact that the null space and the row space are orthogonal to each other. Okay? So if you sort of pictured them in, I don't know how you would actually picture them. You could picture them if they were single lines in R2, then that would be, orthogonal lines oriented somehow or other. This is like some higher dimensional version of this. And we've got the same decomposition, or at least the analogous decomposition on the right? So our codomain Rm is the direct sum of the column space and the co-kernel. And we now know how things map via A, so A sum n by n matrix. We know how things map by the matrix transformation corresponding to A from Rn into Rm. So what do we know? Well, first of all, we know that all of the images lie in the column space, right? So there are things getting mapped into here. There's nobody getting mapped into there, right? There's nobody getting mapped outside here. All of the images live in the column space. We also know that for every element of the column space, there's a unique thing, this is what we just showed, there's a unique thing in the row space that maps to it. Right? There's not 7 things in the row space that map to it, there's 1. For every element of the column space, there's 1 thing in the row space that maps to it. Every other element in the domain in Rm that maps to our given B looks like this. It's our unique P plus just any old rubbish you feel like adding to it from the null space, right? No matter what you add to it from the null space, you get another solution to Ax equals B, right? All of these points, this unique P plus anything you like from in here, they will all map to B, right? And the reason that holds is because all the things in the null space are getting mapped to 0. All right, this, if you can get, we're going to keep adding things to this little diagram, but if you can get your head around this diagram and the more sophisticated versions of it we build up, you basically understood everything in the unit. That's a slight exaggeration, but only a very slight one. Anybody have any questions? Yeah?
Can you actually visualize what the last proof that we're trying to
That's what I'm trying to do, yes. Yeah, it's sort of a cartoon version of the last theorem. Yeah.
Should be able to do more stuff like this as well, 'cause this is very, very helpful.
This is helpful? Okay, good. I am going to keep doing this. Good. All right. Any other questions?
So just to clarify, right?
Yeah.
So basically, every image we get from the RN maps to something in the column space.
Yep.
There's nothing that maps outside of it.
Nope.
Okay.
Yep.
Good, just making sure.
Yep. The column space is the range. Yep. Is that a question over there? No? Okay. That's not a question.
It's like I'm struggling to understand what this diagram is really saying, but I feel like I just have to go over it again and again and again.
I mean, it takes some staring, right? But it's basically summarizing a few different theorems that we've proved. So have a look. In particular, have a look at the lines. Make sure you can understand why things are mapping where. That's all sort of coming from the last couple of theorems that we proved. Okay, but anyway, I'll leave this as a thing for you to stare at. But it is definitely worth staring, right? If you get your head around it, you suddenly, things start sort of making sense. All right, so if there's no more questions on that, I want to change gears a little bit. We'll come back to this picture of the row space and the column space and all that stuff. But I want to change gears just for about a lecture's worth of material. And we're going to generalize the set of scalars we've been using, okay? And we're not going to do this just because it's fun, although it is kind of fun. There's two very concrete reasons why you would want to do this, right? So far, our scalars have been the real numbers. If you want to do quantum mechanics, which you should, your scalars are the complex numbers. If you want to do computer science, which is also okay, then your scalars are generally elements of Z2. Okay? So I'm not going to talk about quantum mechanics, but I am going to talk about applications to computer science briefly. So we're going to be interested mostly today in vector spaces where your field of scalars is some finite field. And I haven't defined what a field is yet, but a field is just a generalization of the real numbers. Okay, so in the same way that a vector space is supposed to be something that looks like Rn, I haven't really proved that that's what vector spaces are yet, but they are, at least if the scalars are reals. An abstract field is something that sort of looks like R, but might be kind of different from R, but shares lots of properties with R. So the definition of a field, all of these things sort of turned up at about the same time. I'm not entirely sure what year this thing was defined, but it was defined in roughly the 1880s, and that's about the same time that vector spaces were axiomatically defined by Peano as well. So all of these sort of ideas, groups came a little bit earlier, but all these sort of algebraic structures turned up at about the same time in the late 19th century. And a field is the following thing. So there's only 6 axioms for a field instead of 10, so that's the first bit of good news. A field is some non-empty set in which we have 2 operations, right? But the operations are defined inside the field now, right? For the vector space, we had 1 operation between vectors and 1 operation between vectors and scalars. Here in the field, we've just got 2 operations between the elements of the field. So we can call these elements of the field scalars if you like, right? So we know how to add 2 elements of the field together to get another element of the field, and we know how to multiply 2 elements of the field together to get another element of the field. Okay, so we know how to do that for reals. You add 2 reals, you get a real. You multiply 2 reals, you get a real. And so we denote the addition of 2 things by A plus B, and the product of 2 things, just write it AB. And they satisfy nice properties, right? So both operations are commutative. Both operations are associative. Right, so it doesn't matter what order you add or multiply things. It doesn't matter where you put brackets when you add things. It doesn't matter where you put brackets when you multiply things. And the addition and the multiplication behave nicely with each other. Right, so they distribute. So you can expand out brackets in the usual way. And we've got identities for both of these operations. Okay, so there's these special elements of f that we're going to call 0 and 1, but they don't have to be, the 0 and 1 that you're familiar with from real numbers. They're just 0, some abstract 0 and 1. And what does 0 do? 0 acts as the additive identity. So if you add it to something in the field, you get that thing in the field back. 1's the multiplicative identity. So if you take something in your field and multiply it by 1, you get that element of the field back. Right? So a plus 0 is a. 1 times a is a. That's what 0 and 1 mean. That's all they mean. It's elements of f that behave like that with respect to all the other a's in the field. And we have additive inverses. Okay. So this thing that we'll call negative a, such that when I add it to a, I get 0. Right? So every element of the field has a negative, if you like. So this sort of allows us to say that you're taking this thing in the field and subtracting some other thing in the field, but what you really mean is you're adding the additive inverse. Now, you've got to be a bit careful. We can't demand that everybody has a multiplicative inverse because that doesn't even work for the reals. Right? That would be too much to ask. But you can ask that everybody except the additive inverse gets a multiplicative inverse. Right? In other words, put it in the language we're familiar with for reals, everybody except 0 you can divide by. That's all we're saying here. Sort of an abstract version of that.
So is a field more or less just like a group just with 2 binary operations, or is that like really oversimplified?
It's got more structure. It's a group with respect to addition. Right, okay. It's not quite a group with respect to multiplication because you don't have an inverse for 0. But yes, it's a group. It's an abelian group with respect to addition with some other stuff with one extra binary operation shoved on top. Yep. And if you don't know what that means, don't worry about it. Okay. Any other questions? Okay. So look, that's all abstract and stuff, and we're not really going to use the axioms very much. We're just going to think about common examples, okay? So the rational numbers form a field, the real numbers form a field, the complex numbers form a field, a set of integers modulo some prime form a field. Now, why am I being fussy and say integers modulo a prime? Why haven't I written the integers up there? The integer is going to form a field. Yeah, that's right. I don't know how, well, nobody in the integers, apart from, I guess, 1, has a multiplicative inverse, right? The rationals work because you can take 7 and then you can divide by 7, and when you multiply 7 and 1 on 7 together, you get 1. But if you're working in the integers, there's nothing in there that you can multiply by 7 to get 1, right? Because the 7th is missing. Okay, so the integers aren't a field. The rationals are sort of, I guess, the smallest familiar field that we play with, but an even smaller one that's actually quite important, quite interesting, and very practically useful in computer science is integers modulo some prime. And in particular, we're usually interested in p being 2. Okay, so what's modular arithmetic? You are all familiar with this because this is how an analog clock works. But what's the point of it? Well, if you're sitting in ZP, then addition and multiplication are just basically exactly what they would be if you were sitting in Z. But when you get your answer, you subtract off all the multiples of P. Okay? So it's just, you're basically only interested in the remainders after you've subtracted off the multiples of P, so that your answer always falls in the set 0 to P minus 1. Right? So ZP, if you think of it as a set, is the set 0, 1, 2, blah, 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 up to P minus 1. So if P is 2, we're just talking about binary numbers, right? 0 and 1. So I'll let you think about what the multiplication table is for Z2, but if we can think about it for Z3, it's a fairly concrete kind of thing. So what would we get? If we add 0 and 0, so we're in Z3, so the addition table here is going to tell me, right, the thing in here is 0 plus 0. Now 0 plus 0, fortunately, is 0, right, so there's nothing too complicated. And because of the way 0 is defined, you add it to any of these numbers, you're always going to get those numbers back because it's 0. That's what 0 does. So these, sorry, that's 1 and that's 2. So the only interesting numbers are sitting in there. That's not a 0, that's just me highlighting that area. So 1 plus 1 is 2. 2 still lives in this set. So 1 plus 1 is still 2. Right? It's not in Z2, but in Z3 it is. Now, 1 plus 2 is 3. 3 does not live in that set. So what I have to do is subtract multiples of 3 until I get back into that set. Right? So 1 plus 2 is 0. And 2 plus 1 is 0 because addition is commutative. So what is 2 plus 2? 1. Good. Right? 2 plus 2 is 1. Go and tell your grandmother. All right, or your grandfather. So, multiplication. 0 times 0 is always 0. Those ones are easy. 1 times anything is just that same thing back. So 1 is 1, 1, 2 is 2, 1, 2 is 2. So the only interesting spot in this table is 2 times 2, right? And 2 times 2 should be 4, but just like in the previous example, 4 isn't 4 because we're in Z3, it's 1. Okay? Now, the definition, just as a remark, the definition of ZP given above does make sense for any natural P, right? It's not that the definition doesn't make sense, but it doesn't satisfy all of the field axioms unless P is a prime. So that's why we're going to only be interested in the case where P is prime. And I'll let you think about what happens when P is not a prime, what goes wrong. And I think on the problem set, you can prove that Z4 is not a field. All right, so have a think about what axiom or axioms go wrong when you try and consider Z4. Okay? All right, now, so that's all fields. Now, why do we care about fields? Because this is a course in linear algebra. Well, we want to take fields and make vector spaces where the fields act as the scalars. Okay? Now, you can do that with a completely abstract vector space. You can take our 10 vector space axioms and you can just say the scalars live in a field instead of in the reals, and everything works. Right? Literally, everything we've said so far still works. So if you take Heiko's algebra unit in third year and he says, why doesn't, or asks you, why doesn't Tim talk about vector spaces over abstract fields, you can say he did, right? Because even though we pretended like all our proofs were for the reals, actually everything we've done so far works for abstract fields. Okay? There is some stuff we're going to do later when we talk about inner products, etc., that doesn't work for arbitrary fields, but everything we've talked about so far, which is just the vector space structure, that works for abstract fields of scalars. Okay, now what's the most concrete way you can make a vector space over some abstract field, where the scalars are some abstract field? You can just take n tuples. Okay, so you just write down vectors of length n, right, n entries. You define addition and scalar multiplication in the same way that we did for the reals, right? So entry-wise. And you can play exactly the same game you did for Rn, you just do it for Fn instead, right? Everything, all the manipulations still work. All right, let's do a poll. So here is Z5. I've written down the multiplication table, but there's one entry missing. What is that missing entry? All right, what is that missing entry? All right, this is good. This seems like people find this easy, which is good. So the question is just, what's 3 times 3 in Z5? 3 times 3 should be 9 if you're working in the integers, but 9's not an element of Z5. Right? Z5 is just the numbers 0 to 4. Right, that's what Z5 looks like. So addition in Z5, or sorry, multiplication in Z5, this is 9 mod 5. But another way of saying what's 9 mod 5 is just what's the remainder if you divide 9 by 5. That's what mod really means. So 9 mod 5 is 4, right? So it's actually primary school stuff. We're just talking about remainders when you divide, but it's got fancy language. And I actually I did teach this stuff, not the vector space side of stuff. I did teach modular arithmetic at my son's primary school because I figured they know about remainders and stuff, and it didn't go very well. But, but in principle, they should have known what I was talking about. Okay, so the answer is 4. All right. So let's look at some applications of this, and we're going to consider just Z2 now. Right? So if you're doing computer science, that's really what you're interested in, because what you want to do is send bit strings down some piece of fiber optic cable or something, however that's done. I'm not entirely sure. But that's the idea, right? So we want to communicate information over some distance. So picture sending stuff through the internet, right? Packets of zeros and ones. And because the real world isn't perfect, there's going to be interference when you try and do this, and there's going to be errors. And coding theory, which is a big business, and it's actually kind of it's a fairly nice, I've never worked in it, but it seems like a fairly nice branch of sort of computer science, discrete maths, where you play with vector spaces over finite fields, right? And the idea of coding theory, apart from getting to play with nice maths, is that you want to construct ways of transmitting data in a robust way, right? So that if an error occurs, you can tell that an error has occurred. And even better, if an error has occurred and you've diagnosed that an error has occurred, you can repair it. Okay, so that's what we're going to do, right? Just using maths. So you give up on the engineering side of things and you say, right, there are going to be errors, no matter how well we do this, there are going to be errors, but we're going to build our system of transmitting the messages in a sufficiently robust way that when errors do occur, we can tell they occurred and we can fix them. And the idea, that seems like you're getting a free lunch, that seems like it shouldn't be possible. The reason it works is because you make the messages you send contain redundant information. Okay, so you make the message you want to send, you've got the message you want to send, you make it a bit bigger, and the extra information in that longer message is what you need to be able to tell whether an error occurred, and if it did occur, where it occurred. And the nice thing about working over Z2 is if one of your bits has an error in it, right, and you know that bit has an error in it, you know what the bit should be. Because if it's a 1 and you know there's an error, then it should be a 0. And if it's a 0 and you know there's an error there, then it should be a 1. So you can fix it easily. Right? Okay. So let's think about Z2, 3, just to be concrete. So first question is, how many elements does Z2, 3 have? And we should list them all, and it would make more sense to write that backwards. right? Because after we've listed them all, we know how many we have. We don't need to know how many we have before we list them all. But, all right, how many are there? How many words can I make of length 3 from an alphabet of size 2?
8.
8? Hands up for 8. Is that for anything else? Yep, 8. All right. Maths isn't a democracy, but in this case it worked. So let's just think about all the places you can put a 1. Right? Then we'll think about, that's if you've got 2 zeros, all the places you can put a 1. Now let's assume you've got 2 1s. What's all the places you can put a 0? And then the case where there's no zeros, okay? So the first entry is where you roll zeros. The next batch of 3 entries is where you have 2 zeros, then the next 3 have 1 0, and then the last one's no zeros, okay? That's all of the elements of this vector space. And in general, what does ZP to the n have? How many elements? Yeah, p to the n, right? So you got n entries. You can put any number from ZP in there. There's p things in ZP. So one seemingly strange thing after you get used to Rn, one strange thing about these vector spaces is that they're all finite sets, right? Every interesting vector space over the reals has uncountably infinitely many elements in it. But these vector spaces are actually just finite sets. Okay, they're just discrete bunch of points. Okay. So let's consider the simplest case. Suppose we've got a 3-bit code word, right? So n is 3. We've got a 3-bit code word. And suppose that our message that we're trying to transmit is the word 011, right? But some error occurs, right? So I try and send 011 to somebody sitting up the back, but what they receive is 010. So if my space of code words is just Z23, then there's no way of telling that an error has happened, right? Because this is a valid element of Z23, but so is this. Right? So there's no way of telling whether or not an error happened. So the idea is that we enlarge, if we want to send 3-bit messages, we enlarge Z23 a little bit, and we construct 4-bit code words. Right? This is the sort of simplest way you can do error checking. And what we do is we append to the end of our message a thing called a checksum. So what's the resulting set of code words? So let's consider elements of Z23. They look like that. And then we're going to add this extra 4th bit. And what's the extra 4th bit? It's this thing called a checksum. And what is it? It's the sum of the first 3 entries. Okay? So you add this 4th bit. So we're looking at a subspace of Z24. Not Z23, but a subspace of Z24. All right, so this is all these guys. These live in Z2. And this is a subspace of Z24. Okay, now, because the 4th bit's completely fixed, this isn't all of Z24, it's just a subset of it. And how many elements in this subset? It's not 16 because the 4th bit's completely fixed. 8, right? I can choose the first entry, the second entry, and the third entry to be whatever I like, but then the 4th entry is fixed. Okay? So this is a subset of Z24 that actually has the same size as Z23. And what I can picture is that this first 3 entries is really my code word, and this 4th bit is just some way of telling whether an error happened. So what do these messages look like? I'm going to get lazy, and I'm going to forget writing all the brackets and the commas because it gets tedious. So when I write 0, 0, 0, 0, I mean, you know, the vector 0, 0, 0, 0, but hopefully that's clear. Then if I consider 0, 0, 1, and I add this extra entry to it, it's going to be the sum of these first 3 entries, so it's a 1. And likewise, if I look at 0, 1, 0, and this checksum, it's going to be 1. And 1, 0, 0, and I look at this checksum, it's going to be 1, because the sum of these 3 entries is 1 plus 0 plus 0, which is 1. And then I can look at 1, 1, 0. Now, what's the sum of the first 3 entries here? 0, right? Because 1 plus 1 is 0. Because we're in Z2. So this is 1 plus 0 plus 1, that's 0. 0, 1, 1. 1 plus 1 is 0. 1, 1, 1. What's 1 plus 1 plus 1? 1. All right? Good. So that's what this subset of Z24 looks like. And now, let's say that we try and transmit the same message, 0, 1, 1, but we've added this checksum to the end, 0. Right? Now suppose I try and send that message, and the person up the back receives 0, 1, 0, 0, right? So there's been an error in the 3rd bit, right? They can tell there's been an error in the 3rd bit because the checksum's wrong. So they don't know where the errors happened. We'll talk about that on Thursday. But they know where an error has happened because the checksum's wrong. Now, this only works if you have 1-bit errors. If you get 2 bits wrong here, you still can't tell. But there are fancier versions of it that do work, right? So you can build as many checksums as you need to so that you can detect as many errors as you like. And then in practice, what you hope is that the probability